So the Heisenberg uncertainty principle that we looked at last time ushered in our world of quantum mechanics, and that's what we're going to talk about here. We know that electrons don't really move around in orbits like we saw with the Bohr model. With planets, which do this, we can know where they are at one point, we know how fast they're traveling, we can predict where they're going to be at any other point. We don't have that luxury with electrons, okay? Heisenberg's uncertainty principle let us realize that we can't know exactly where they are, but we can know a region in space in which you have a high probability of finding an electron. So we can kind of zone out a little bit and say in this region, we know that the electron is going to be. The Schrödinger equations, we won't look at the equations. The Schrödinger equations are mathematical expressions that define the area in space where you would have this high probability of finding the electron. We would say it has a high electron density in this area. So let's just imagine, let's look at an atom for a little bit, and let's say this atom had an electron in it, and we're monitoring and say, okay, the electron's here, we know that, we don't know where it's going, but we know it's here. The electron is now here. We don't know where it's going, but we know it's here. And we know it's here. And we keep locating that electron, and we find that that electron is kind of in an area where you just have a high probability of finding it, okay? And that if we look out here, we're not seeing it, so we can know where it is. What we have is these mathematical equations that take into account the dual nature. They take into account the wave nature of the electron. They take into account the particle nature of, I didn't spell that right, but that's okay. Particle nature of the electron. It takes into account that dual nature and is able to mathematically define regions in space where you're going to find the electron. We say that it has a high electron density. That's what's kind of represented by this map. We don't have electrons out here. We have a lot of, because we spotted them here a lot, we'd say that had a high electron density. Now, a mathematical equation that defines something, a shape, is not unknown to us in just the algebra world. Remember the equation y equals mx plus b? That defines a line and a slope of the line and where it intercepts the y-axis, which is b. We know that a mathematical equation can define things like that. Well, these Schrödinger equations are very complex that require multiple semesters of calculus. So Calc 4 is a typical prerequisite when we start looking into these Schrödinger equations. So they define three-dimensional regions in space where you have a high probability of having your electron. Okay? I already told you that. They account for the dual nature, and this is what launched this idea of quantum mechanics, these Schrödinger equations. Eventually we'll be able to narrow all the way down and define what we call, and no longer call orbits, but orbitals. So they took a play off that word orbit and they call them orbitals where you have this high electron density. Now, I already said that. What comes out of this that we're really going to focus in on is the quantum numbers. There are 4 quantum numbers that come out of these Schrödinger equations. So while we'll never look at the equations themselves, we do want to look at and examine these numbers that are derived out of these equations, because these numbers will tell us where that electron is. So I want us to kind of use an analogy as we talk through these quantum numbers. And the analogy that I'm going to keep on coming back to is we're going to imagine, here's our imagining, okay? We're going to imagine that each one of you, everybody in the world goes to college, all right? That's the first imagination, all right? The next thing we're going to imagine is that they all live in dorms, okay? So there's our second imagining. And the third thing is they, of course, live in a dorm room with a couple, with a roommate, okay? So you have 2 of you living in there. So that's our imagination. So what we're going to be able to do is we're going to define with these 3 numbers which campus you live on. Are you at the University of Kentucky or are you at the University of Tennessee? All right, so you're going to have a number that defines which campus you live on. Then the second thing, it's going to narrow it in a little bit and say which dorm are you in. Okay, so you got a second number that kind of defines your dorm. And then you're going to have a third number that says which room are you actually in. Okay, that's the first three numbers there. So the first three numbers tell you where that electron lives. It's kind of narrowing it in further and further until you get right down to the orbital it's in. And the fourth number is kind of telling you what you're doing. All right, so that's what those numbers are going to tell you. And we won't look at, sorry, let me back up. We won't look at the spin quantum number, what that electron is doing, until later, after this chapter. Right now, as we finish up this chapter, we're just looking at those first three, N, L, and M sub L. Let's start with the first one. The first one is the principal quantum number N. And the principal quantum number N is telling the big, broad picture of where that electron is. We've got to narrow in our focus as we go, but it's the first kind of, what campus are you on? It's kind of that broad, okay? The values of N we've seen before when we talked about Bohr's hydrogen atom and the model there. He used these quantum numbers, N. And N starts with a value of 1, and then it goes to 2 and 3 and 4. So they're whole numbers or integers up from the number 1. And what is this number telling us? It's telling us a couple things. The first thing is it's telling us its relative distance from the nucleus. So when it's N equals 1, it's close. When it's N equals 2, it's a little further out. When it's N equals 3, it's a little further out from there. So that is the first quantum number that it's the first thing that quantum number is telling me is the general distance out from the nucleus. The second thing it's telling us, well, it's further out, the bigger the N. The further out it is, the higher its energy is. So when it's close, it has less energy. As it moves out, it's more energy, and so forth. Now, we saw that with the Bohr model because we had a mathematical expression for, I actually came up with an equation where you could have how much energy that electron has in each one of its N values. So the two things that you know about two electrons that have different N's. The smaller the N it is, the closer it is to the nucleus. The bigger the N it is, the further out it is from the nucleus. The smaller the N is, the less energy it has. The bigger the N is, the more energy it has. So this tag that we tag onto the electrons first is going to tell us the N value. Now, any two electrons that have the same N value are said to be the same principal shell. Now, let's go to our analogy. Everybody goes to the university. The first value is which university are you in? So if you had the same, value of this quantum number, you would know you went to the same university, okay? And somebody else had a different value, they're at a different university. Well, with the N's, every electron that has the same N is said to be in the same principal shell. Sometimes we throw the word principal away and just call it the same shell. The N equals 1 shell, the N equals 2 shell, the N equals 3 shell as we get further and further away. Now, revisiting our hydrogen atom, this is the energy that an electron has when it is in its different shells. And this is the equation that we have. I said I thought we referenced this before, but I don't think we did. I think we're just now seeing it right here. Okay, so the electron has an energy. Now this only works for hydrogen atoms, so that's why it says hydrogen up there. That is defined by the N that it's in. The N that it is in. Okay, so we have an N equal 1. We would put down there in the denominator 1 over 1 squared, and then the energy of the electron would be equal to the Rydberg constant there. That's what that R sub H is called. Okay, it's called the Rydberg constant, and for hydrogen it's 2.18 times 10 to the minus 18. N equals 2, we put a 2 in there. 2 squared is 4, so we take that number and divide by 4, or multiply by 1/4. When N equals 3, we'd put a 3 in there and square it, so we would multiply by 1/9. And what this gives us is this progressive energy. Now notice how when N equals 1, the value is negative 2.18 times 10 to the minus 18. An electron has a negative energy when it's associated with an atom. And the closer it gets, the lower its energy. So when it's N equals 2, okay, it is not quite as negative. Negative 5.45 times 10 to the minus 19. That's what happens when you put N equals 2 in there. And then we have N equals 3 and N equals 4, and we could calculate the energy of an electron. But what I want you to really note is that the bigger the N, the higher the energy, because we are dividing by a bigger and bigger value. And I've underlined hydrogen just so you know if you're ever asked to calculate the energy of an electron, you can only use this equation if it's for a hydrogen atom. All right, ready to go to the next value. The next value is L. L is the angular momentum quantum number. So we're tagging these electrons with where the electron lives. The first one is telling me the N, where it is in general from the nucleus. The second one is like saying, okay, yeah, I am at the University of Kentucky. What dorm do you live in? I live in Woodland Glen 4. So you've kind of narrowed it in a little bit more and telling a little bit more information. That's what this number does, is it narrows in a little bit more about that electron of where it lives. Now the values of L are dependent upon the value of N. L can start at 0 and it can keep going up by increments of 1 until you're 1 less than N. So L up to N minus 1. And this tells us the shape of the orbital. Now I'm going to show you the shapes in another lesson, but it is going to tell us the general shape of that. It's also going to give us a name, and we're going to see the name here. When we know the value of the L, we're going to be able to say a name for what we call a subshell. Okay? So all electrons that have the same N tagged to it and the same L tagged to it are said to be in the same subshell. So that'd be like saying all the people at the University of Kentucky who live in Woodland Glen 4 are in the same dorm. Okay, you're in the same dorm. All electrons have the same N and the same L are in the same, what we call a subshell. Now these subshells have the following names, okay? So we got to name them. We don't name them by their number. They have a number. These numbers came out of the Schrödinger equations, but they have names. So you need to know these names. When L is 0, it's called an S subshell. When L is 1, it's a P subshell. When L is 2, it's a D. When L is 3, it's an F. And then after that, it's alphabetical order, G, H, I, J, K. You probably will never have to name something beyond an F. You've heard of F orbitals, F subshells. Now, not only are subshells named by these names, the orbitals that are contained within those subshells are also named by these names. So you can talk about a D subshell and you can talk about a D orbital. All right, so that the same language is used for both. Okay, so now let's go into the front. We have a N of 1. That's the smallest possible N that we have. When N equals 1, our L's are dependent upon that. So let's just start kind of deriving this. When N is equal to 1, what are your values of L that you can have? Well, L starts at 0, that's the smallest one you can have, and it keeps increasing until you're 1 less than that. If it keeps increasing until you're 1 less than that, well, that's 0 and I'm done. And what is the name of that subshell? The name of that subshell is an S subshell. Okay, so that's the first one. Then we can go out a little bit more and say, well, N equals 2. What are my values that I can have of L? The smallest L we can have is 0. This 0, or we can go up to 1 less than this, we can have a 1. So in the second shell out, we have 2 possible subshells. What are their names? S and P. So we have 2 subshells in the second shell. And you keep on deriving this, and we'll do some more of it here in a little bit. Okay. So if you have a shell that's N equals 4, I want you to think about, following this model, what are all the names of the subshells that can be in the N equals 4? I'll let you work on that, and then we'll check your work. Okay, well, hopefully you answered D and everything's right with the world, but just in case you didn't, let's go to N equals 4. We know that L equals 0, 1, 2, and 3, and what are the names of those? S, P, D, and F. So whatever number you have, that's how many subshells you can have. How many would we have for N equals 3? We'd have 3 subshells, S, P, and D. All right, ready for the next quantum number. angular momentum quantum number, it's M sub L. That's the name of it. M sub L is dependent upon L. It can go from a negative L up to a positive L. Now let's just stop and think about this for just a minute. Where do these numbers come from? They are derived out of the Schrödinger equations. So these Schrödinger equations were complex mathematical equations that are defining three-dimensional shapes. And out of these equations that they have incorporated in the wave nature and the particle nature of these electrons, these numbers come out. So it's not like somebody said, these are some cool numbers, let's pull them out. Okay, they came out of these equations, but the M sub L can go between a negative L up to a positive L. So it's really tied to your L value. Okay, and what does it tell me? It tells me the orientation in space of a specific orbital. So we're really getting all the way down to exactly where the electron is, all the way down to the orbital. What we would say, it'll also tell you the number of orientations it has, depending on how many M sub L values you have. How many M sub L values do you have? Depending upon how many you have, that's how many orbitals live in a certain subshell. This would be like, going back to our analogy, we know we're on the University of Kentucky campus. We know we live in Woodland Glen 4. The M sub L would say, well, how many dorm rooms are in there? And which dorm room do you live in? So you're narrowing it all the way down to a specific location, all the way to the dorm room in a sense with this, okay? So any electron that has the same three values of N, L, and M sub L, we would say are in the exact same orbital. This would be like you saying, I am at the University of Kentucky, I'm at Woodland Glen 4, and I am in the dorm room 105. Don't know if there's a 105 there, but that's the dorm room I live in. I've narrowed it all the way down. And everybody else who has the same values of N, L, and M sub L that I have are at the University of Kentucky, are in Woodland Glen 4, and also live in my dorm room. Okay, so you can have people with the exact same address, and that's exactly what the electron is. There's three numbers are telling me where the electron is, narrowing it down all the way to a specific orbital. Okay, so let's derive all the possible values of N, L, and M sub L on this. You've got this sheet in there, but I'm going to do it right here on our screen. All right, so we've started it up here, but I'm going to kind of just revisit and re-go with this. Make my pen work here a little bit better, get some ink going. All right, so N, the first value of N, the smallest value of N you can have is an N of 1. The L only is 0 because it goes from 1 up to, 0 up to N minus 1. That is an S subshell. Then we have M sub L. M sub L can go from a negative L up to a positive L. Negative L up to a positive L. Well, then we have a 0. Negative 0 up to positive 0. We only have a 0 here. So that's the only possible M sub L for that L. What is this telling me? This is telling me the number of orbitals in this subshell. So this is telling me my subshell. Okay, this is telling me the orbital, and this is telling me there's only one orbital there. Now this looks like a 0 to me, but it's the number of numbers you see, not what is the number here. I see one number here, happens to be a 0. There is one orbital in the S subshell. So let's move out to the next N. An N of 2. The values of L are either 0 or 1 because this can go up to 1 less than that number. This is a sublevel of either S or P in this N equals 2 shell. So there are two sublevels. So we're at a campus, a university that has two dormitories, okay? This campus is very small. It only has one dormitory. This campus, bigger, has two dormitories. Now let's go into dorm rooms in the dormitory. M sub L. This is only 0 because it goes from a negative L up to a positive L. But this is a negative 1, a 0, and a 1. How many numbers do you see there? I see 3 numbers. So there are 3 orbitals in the P subshell. That's what that's telling me. So this is a bigger dormitory. This dormitory has 3 rooms in it. That's a tiny dormitory. It only has 1 room in it. All right, very little. Let's go out to N equals 3. When E equals 3, we have a 0, we have a 1, we have a 2. This is our subshells. We have a S, we have a P, and we have a D subshell. So these are the subshells. There are 3 dormitories in this campus. It's a bigger campus. In the first dorm, it only has 1 room. In the second dorm, there are 3 rooms, 3 orbitals. And then D goes from a -2 up to a +2. We have got 5 numbers, 5 numbers there. There are 5 D orbitals in a D subshell. Now we'll go one more out. That's all I got room for. One more out. We're 4. Now in the world of our electrons, an electron that has a value of 4 we know is further out from the nucleus. All right? This is a different campus somewhere that has dormitories 0, 1, 2, and 3. All right? These are the sublevels in the 4th shell out. This one's called S. This is called the P sublevel or P subshell, D, and F subshell. So this is 1 orbital in the S. These are 3 orbitals in the P. These are 5 orbitals in the D. And then we do our F. Our F goes from a -3 up to a +3. How many numbers do you see there? Well, there are 7 numbers written there. So there are 7 F orbitals in the F subshell. So F subshell. So when you have N of 4, L of 3, and any one of these you could choose from, you have defined a specific orbital that an electron lives in the 4F subshell. So we have a bigger campus. There are 4 dormitories. This dormitory is pretty big. It's got 7 dorm rooms in it. Okay, we're narrowing in our focus of where that electron is. The first one tells us the general region. The next one is the sublevel. Then the third one is the actual orbital that the electron is housed in. So, 2 things that you should be able to do. Number 1 is if I told you the name of an orbital or name of a subshell, you should be able to give me the quantum numbers for it. The other one is you should be able to tell me what's allowed. If I look at this, is there such thing in the 3rd shell as an F subshell? No, I don't see it anywhere. I have S's, P's, and D's. There's no such thing as an F. Okay? I can also look over here and say if I'm in the P subshell, is there an orbital called -2? No, there's not. So you ought to be able to know what's allowed and what's not allowed. So over here is an example that you're going to stop and you're going to think about in terms of this table and deriving is which one of those is not an allowed set. You can't just have any possibility. Which one's a not an allowed set of quantum numbers? Well, if you look at that and you compare it with what we have actually drawn out, you can see that there is no such thing as a 2, 2, and a -2. Here's a 2. Well, there's no 2 because I can only have 0 and 1. So A is not allowed. All right, 3, 2, 0. We can have a 3, 2 with a 0. That's fine. I've got a M sub L of 0 in the D subshell in the third shell. All right, how about 4, 1, -2? Well, you can have 4 with a 1, that's allowed, but there's no -2 when that's 1. We can only go from a -1 to a +1. So C is not allowed. The second question asks you to give us a good set of quantum numbers if you are an electron in the 4p subshell. So you're tagging this electron with allowable values of N, L, and M sub L if this electron is in the 4th shell and the p subshell. Okay, so for this one, you should have picked B and C are allowed. Why is that? Well, if it's P has an L of 1. So in the 4th shell, the first number tells you the 4, okay, so we know we're in the 4th shell. We're in the P subshell, so that's an L of 1. And what are the allowable M sub L's? We could have it be a -1, a 0, or a 1. So any one of those would be okay. So in B I have 4, 1, 0. In C I have 4, 1, negative 1. Another allowable set could have been 4, it's in the fourth shell, 1, it's a P, and 1, it's in the third one of the choices that I had to choose from for that. All right, so in this whole series, what we're talking about is the quantum numbers N, L, and M sub L. They tell you the shell, the subshell, and the orbital that an electron has. An electron can be tagged with these three numbers that tell where that electron is, M, L, and M sub L. They say this is where it is as far as its shell, this is where it is as far as its subshell, and now I've defined where it is right down to its orbital, this region in space where you have a high probability of finding the electron. We have a high electron density.